Price acts as our client sponsor, and for this project have tasked us with redesigning their VCRA EC damper in order to reduce the cycle time by 50%. The current design is complex with a lengthy assembly time and the need for part outsourcing, which incurs variable costs. Our team's goal has been to reduce overall costs of manufacturing and assembly through a simplification of the design. The original VCRA EC damper is made primarily of in-house sheet metal material, and the overall structure can be decomposed into 4 parts: the fixed cable, the adjustment mechanism, the damper blades, and the housing. The current design uses a flexible cable which is composed of multiple parts including a spring, a worm gear, cotter pins, and more. For adjustment of the damper, the customers have access to a screw which rotates the cable, rotating the worm gear at the end, which ultimately opens and closes the damper blades. This design has remained popular among consumers over the years for its reliability and ease of adjustment. The damper blades are made of in-house sheet metal and are cut in half circles, which allows them to open in a butterfly style as they pivot about a center point. This helps conserve space in the ductwork so the system does not interfere with the plenum. These blades are held within a sheet metal housing which slides onto the plenum to be used in HVAC systems around the world.
So how can we cut down on manufacturability and reduce cost for one of our biggest HVAC company in the world? Well, let's take a look. Before coming up with a solution, our team came up with a few constraints that we believe were best for the design of the project. This was a meticulous process, but there were some things that we considered to be fixed during the design process. This was mostly because of the consideration needed to be made from our stakeholders, as well as few things we considered to be essential to the project. First, the cable length should be used needed to be fixed to a specific length. This is to ensure that the cost can be accurately conveyed in a cost analysis. Second, the overall cost of the design should not exceed the current cost under any circumstance. If your material cost is to be higher, it must be compensated for by decreasing labor cost. Third, the design must be relatively easy to manufacture and allows to the possibility to automate. Fourth, all stakeholders must be considered, and it is important to ensure the consumer is still satisfied. We came up with 2 different designs that may change how the damper could operate. Knowing these parameters, one new design used a rack and pinion to transfer rotational motion into translational motion in order to push and pull the damper blades open and closed. The original plenum does not require restructuring, so the main vessel remains intact with its in-house materials. The rack and pinion prototype is instead 3D printed to illustrate the changes that were made to the design and are fully implemented into the damper plenum system. We will call this design 1.
Here we have design 2, which builds off of the original cable design but uses a single flap instead of a butterfly style of opening and closing. This damper would be operated by an elbow joint and a single rod which would sit behind the flap. This design had the potential to decrease manufacturing costs because it is a much more simple design than the original VCR8 EC damper. However, it was not chosen as our final solution due to the issue of the plate hitting the back wall of the plenum when being rotated to increase airflow.
After considering both design options, we decided to choose the push-pull mechanism. There are a few reasons why we chose this option. This design focuses on the redesign of the damper operating drive mechanism, since it is the most costly part of the current design. It will be adjusted from the outside of the damper in the same manner as the original design. It maintains full range of airflow through the damper. This design will reduce the number of steps for assembly, which will reduce the cycle time. It will also reduce the cost of material for the drive mechanism. Here you will see a parts list and cost table of the original cable assembly and the push-pull drive mechanism. The cable assembly parts include a flexible cable, adapter sleeve, a cable bracket, operator screw, operator nut, cotter pin, and 2 bracket screws. The total cost of material for the cable assembly is $362. For the push-pull drive mechanism, the parts include a rotating rod, a damper interface gear, gear rod support, pinion gear, operator screw, bracket mount screw, cable bracket, and operator nut. The total cost of material for the push-pull drive mechanism is $259. The total cost of the existing VCR 8EC design ranges from $6 to $6.69. The total cost of the new VCR 8EC design ranges from $4.97 to $5.66. The price reduction from the original design to the new push-pull drive mechanism is $1.03, which is a cost reduction of 20%.
Here we have included a screen share of the simulation that we had for the push and pull design, also known as Design 1. You can see that the rack and pinion solves the problem of locating rotational motion into translational motion so that the dampers may operate at full effectiveness. Thank you for your time and consideration. We would like to thank our client sponsor, Price Industries, for giving us the opportunity to work alongside them for dampers at such a large scale. We learned the aspect of team building at the most professional scale by being able to collaborate on this project, and it doesn't get any more real than that. We would also like to thank our mentor, Dr. Hu, for his generosity, consideration, and feedback throughout the course of the academic year. Having a mentor has been especially helpful, and it was very important to us that we were able to bounce off ideas from someone who is so experienced. Finally, we would like to thank our university and Dr. Pittaparty for setting up this incredibly enriching experience and giving us the platform to troubleshoot and problem-solve a real-world problem. We hope you all have learned some of the design process and how we saw fit to reduce cycle time and overall cost. Thanks for watching.